or host so that you can present the screen.
Yes, sure.
Okay. Okay. So should we start?
Just give me a minute.
Okay, okay.
Okay, fine. We can start now.
Okay. So I would like to take this opportunity that as my privilege to introduce our keynote speaker, Dr. Puneet Kumar Jain. He is currently working as an assistant professor in Department of CSE, NIT Rourkela, Odisha. Earlier, he has served as an assistant professor at the LNM Institute of Technology, Jaipur, and JP University of IIT Solan. Dr. Jain has completed his PhD degree at Indian Institute of Technology, Jodhpur in the year of 2018. MTech in IT from Delhi Technological University, Delhi, India in 2011. He graduated with BTech degree in Computer Science and Engineering from Engineering College, Bikaner, India in the year of 2009. Dr. Jain is having research interest in the field of biomedical engineering, where his research focus on the healthcare technology and algorithm development, aiming to advance patient diagnosis, assessment, and treatment. His area of research interest also include image processing, time frequency analysis, medical imaging, signal and data compression, machine learning. He has published his research in the peer-reviewed and SCI indexed international journal and conferences. He is also a reviewer for various renowned international journals, including the Biomedical Signal Processing and Control, Computer in Biotechnology and Medicine, Health and Policy, and the various international conferences. So this was just a brief introduction of his tremendous work experience. Now I would like to invite Dr. Puneet Kumar sir to start with his lecture. Sir, please start.
Yeah,
Your
thank you for
screen is visible, sir.
thank you for introducing. I hope that my screen is visible now.
Yes, yes, your screen is visible.
I will just test that my screen is being changed or not. So I am changing the slide. Is the slide changed?
Yes, sir, changing.
Okay, great. So what I have around 1 hour 15 minutes.
Yes, yes, sir, sure.
Okay. Okay. So to all the participants, if any particular doubt is there on any particular presentation, you can intimate me. I will try to resolve that particular doubt on that particular slide.
Yes, sir,
So in this slide, I am going to discuss about the role of machine learning models to monitor cardiovascular functions. Majorly in this slide, there are two broad areas where I am going to focus. One is how to use the time frequency analysis for various signal and image techniques. And then I will discuss few techniques on which we have worked, my team has worked to resolve certain issues available in the cardiovascular monitoring. And at the end, I will discuss the challenges available in this particular field, the available data sets, some few research papers by which if particular person is going to start or is in this particular field, he can also look up on those particular content. This is the roadmap of this presentation. First, we'll discuss a little bit about the introduction of role of AI in healthcare and the cardiovascular system. Then we will discuss about the dosing algorithm, classification algorithms, including the machine learning algorithms and the deep learning algorithms. And finally, I will conclude the slides. So first, let us discuss about the role of AI in healthcare. Those who are working in this area or who are interested in this, probably they may have come up with various applications of machine learning as well as deep learning techniques for various medical applications. Now, when I'm saying the medical applications, as an engineer, we consider the data either as in a format of the in the tabular format, a 1D data or a 2D data, right? So that depends on what kind of sensors we are using to analyze that particular organ. So different modalities have been used to analyze various organs. These are few examples I am describing here. Like this is one example where the machine learning has been used to classify the Alzheimer's disease using the brain MRI images. So in that task, there are various steps here, including like kind of pre-processing, segmentation, and then to do feature extraction and segmentation. This is another area where we place various set of electrodes on the abdomen of a particular means the mother and to analyze the electrical activity of the fetus, and this system is called as electrostereography. In another example, many of you might have heard these kind of things that we can use the chest X-ray images to identify is there any symptoms of pneumonia is present or not. So these kind of things can be used for the COVID detection. Also, what is the impact of the particular disease and so on. Then there is another area where there are again different modalities. The heart functionality can be analyzed either through electrical perspective or mechanical perspective or the image modalities, right? Like we can use the ultrasound images and various other techniques of the images to analyze the internal characteristic, the functional characteristics of a heart. So probably many of you might have gone through these kind of testing like the electrocardiogram, which is known as ECG, and phonocardiogram known as phonocardiography, right? This is another example where the ultrasound images of the breast is being used to detect is there any cancerous cell or not. Another example where by analyzing the structure of the bones and the maturity period of these bones, we can estimate or we can assess the bone age, or we will try to estimate the human age. So these are only few fields where right now the means AI, ML and DL algorithms are being used extensively. In this particular presentation, I am going to discuss in detail about how to use various signals related to the heart to analyze the functionality of the heart. There is one reason because this is the research area where I mostly work. First of all, we have to understand is that the heart is the most important organ of the human body, which supplies replenish oxygen and also remove the waste from each cell. And see, there are around 37.2 trillion cells in the body. In addition to that, heart works very smartly. Means whenever our body or due to the pressure on the mind, whenever our body requires a high amount of the oxygen, blood tries to provide that requirement to complete that requirement by pumping at a higher rate. And in the rest period, the pumping rate get reduced. So means it works smartly as required. It performs according to that dynamically. How so? I'm going to use these two figures. Both are the figures of the internal structure of the heart, but the left structure is describing the locations of various walls and various components, while the right figure is describing the electrical conduction system of the heart. So using these figures, I would like to explain how the human heart actually works. First of all, the journey starts. Okay, there are four chambers: right atriums, left atrium, right ventricles, and left ventricles. First of all, the journey starts by blood flow inwards to the heart. So the blood from the body, the deoxygenated blood from the body will comes into the right atrium from the supravenous cava and inferior vena cava. At the same time, the oxygenated blood from the lungs will enter into left atrium. This is the, you can say, the onset of the one cardiac cycle. What happens in this, when the blood enters into the right atrium and left atrium, what happens is that our blood contains various cations, the positive cations. So what happens? Due to the influx of the blood into the heart, there would be electrical induction or a potential difference will be generated, and due to that, an electrical impulse will be generated. Initially, the electrical impulse will be generated at this particular point called a sinoarterial node. Now, there is a very interesting characteristic of our heart muscle. If you will apply any electrical impulse on the heart muscles, they will contract. Right? Probably that's why you might have seen that if someone's heart get stop working, then we apply the shock. So the basic phenomena is that we are applying the electrical impulse, and due to the particular property of the heart muscles, they will contract. So once this electrical impulse will be towards to the atriums first, what will happen? The atriums will contract. And as I mentioned earlier, blood has already entered into right atrium from the body and left atrium from the lungs. So the blood from the right atrium will enter into right ventricle and left atrium into left ventricle, right? After that, what will happen? The electrical impulse which has been spreaded to the atriums, now using through these Purkinje fibers, it will spread throughout the ventricles. Now again, what will happen? The ventricle will contract. Okay. So once the ventricle will contract, what will happen? The blood from the right ventricle will enter into pulmonary artery, and blood from left ventricle will enter into aorta. Please observe the architecture of these walls, right? This is the tricuspid wall, this is pulmonary, this is aortic wall, and this is mitral wall. The architecture of these walls is such that they only allow unidirectional of blood flow. That means when the right ventricle will try to push the blood, the tricuspid wall will close. So it will not allow the back flow of the blood again into right atrium. Blood will flow from right ventricular to the pulmonary artery to the lungs, right? And the oxygenated blood which enters from the lungs to left atrium to left ventricle will enter into aorta, and then it will go to the body. So that's how one cardiac cycle gets complete. Okay? This is just one complete representation of how the blood flows. If you will follow this particular door, you will understand that how our blood flows from the body. It will enter right atrium, right ventricle, lungs to left atrium, left ventricle, and then again it go to body. So this is one cardiac cycle. Now we can use various signals to analyze these cardiac functionalities. Before that, I just want to explain what are different abnormalities might be there with the heart and what mean by those terminologies. There is one particular wall which separates the right ventricle and left ventricle, that is called a septum. So if there would be any abnormality within the septum, if there is a bypass between these ventricles or between the atriums, that is called septum. If there is bypass in the atriums, it is called atrial septum. Otherwise, it is called ventricle septum, respectively. So in this case, it is called as ventricle septal defect. As I have mentioned, in the normal fashion, the wall should allow the flow of the blood in one direction. But let's say due to the disease, these walls are not able to stop to restrict the blood flow in the opposite direction and the blood flow in the opposite direction, which is not normal. So this kind of problem is called as regurgitation. This regurgitation may occur with any particular wall. There are 4 walls. So according to that, these regurgitation will be called mitral regurgitation, tricuspid regurgitation, and so on. In the normal way, these walls should allow to flow the blood in the normal way. There should not be any restriction in the normal direction. However, if there is a disease and the walls are not able to open properly, then there will be restriction in the normal flow, and that disease is called as stenosis. Again, it may occur with any particular wall, and accordingly, they are called as pulmonary stenosis, aortic stenosis, and so on. This is a very common known heart disease called as myocardial infarction, also generally known as heart attack. What happens in case of heart attack? See, there are various veins, there are various arteries which provides blood to the heart muscle itself, because heart muscles also require the oxygen. So there are muscles to the heart muscle. There are arteries which provides the blood to the heart muscles. If there is some blockage due to some plaque deposition in these arteries, what will happen? The blood would not be able to reach to that particular muscle. In that case, what will happen? Those muscles will start to die, and the normal functionality of the heart will get distorted, and that is called as heart attack or myocardial infarction. Now, to analyze the functionality of the heart, as I mentioned, there are various techniques or various perspectives by which we can analyze the functionality of the heart. So these are just few introduction. The first one is the electrocardiography, where we place the electrodes on the chest, and then we measure such kind of electrocardiogram, where there are various waves, PQ, RS, TU, and so on. Here we are measuring the electrical activity of the heart. As I have mentioned, due to the electrical activity, there is an electrical conduction system, and we are measuring those electrical signals by placing the electrodes at various locations. Another technique, phonocardiography, where a doctor, a medical person generally use a stethoscope. Most of you might have gone through screening through this stethoscope. So doctors try to listen the sounds produced by the heart functionality and try to understand what is there any abnormality or no. This is another technique, seismocardiography, where we use this kind of sensor called accelerometer, right? And accelerometer, as name is suggesting, it is going to measure the acceleration signal which are being imposed at the chest wall due to the functionality of the heart. And that's how we can analyze various events of the heart. Another modality is called as photoplethysmography, which is again very common to monitor heart rate and sometimes for the BP also, where we use these photodiodes and light emitting diodes to measure the blood amount fluctuation in various veins, and then we analyze what is the pressure and what is the heart rate. And this is one imaging modality where we are using means in echocardiography. Generally, the ultrasound techniques are used to understand the internal structure of the heart, how the internal different walls and the structure of the heart is being functioned. Now, if you would like to compare these different modalities with respect to portability, echocardiography is not suitable, right? Because for the echocardiography, we require an ultrasound machine, which is expensive as well as bulky. So not suitable for the portable system. So we have these four options. If we compare them with respect to diagnostic features, there are three prominent modalities: ECG, PCG, and SCG: electrocardiography, phonocardiography, and seismocardiography. Photoplethysmography provides information about the heart, but in a limited manner, because generally we analyze the photoplethysmography from a remote location to the heart, and that's how means it provides limited information about the heart functionality. Now, according to the last parameter, compared to the convenient and easy to operate, we can say the phonocardiography and seismocardiography are the two modalities to analyze the mechanical aspects of the heart, and electrocardiography analyze the electrical activity of the heart. That means these two different modalities will provide different information about the heart functionality. Another advantage with the phonocardiography or seismocardiography is that the systems are convenient to use and low cost in repetitive use. And that's why means the doctors use the stethoscope for the first stage screening. Now, I'm going to discuss about little bit about the introduction of the phonocardiogram, what kind of signal a phonocardiogram is, what is their relevance, and then what is the task as an engineer to do with the phonocardiogram signal to analyze the heart functionality. Okay, this slide is describing certain numbers regarding the heart-wall disease, which can be easily identified and prominently available in the phonocardiogram signal. Heart-wall disease is one of the cardiovascular disease. In numbers, there were around 5 million patients in the US alone, and this number is increasing every year. The fact is, major concern about any kind of cardiovascular disease, not only heart-wall disease, around 50% cases did not diagnose at an early stage. The reason is the symptoms due to the abnormality of the heart are not that much prominent at an early stage, and generally the patient try to avoid them. And once it becomes the prominent, most likely the situation get worsened, where it becomes hard to recover. And out of these 50% cases, there is less likely to survive more than 2.6 years. So the important task here is that using certain engineering techniques can be help the medical fraternities to identify these abnormalities at an early stage. For that, I hope the heart sound signals, analysis of the heart sound signals provides ample diagnostic features to detect various abnormalities with the heart at an early stage. There is a specific reason behind this opinion. The reason is the heart sound signals are produced by the mechanical activity of various components of the heart, specifically the opening and closing of the heart walls, such as the closing of tricuspid and mitral valve. First heart sound is the name, different names of this. First heart sound. These are fundamental heart sounds. Second heart sound is caused due to the closing of aortic and pulmonary valve. So by analyzing these heart sounds, we can identify what is the intensity, what is the frequency of those heart sounds. We can understand these both, and by analyzing those factors, we can analyze is there any abnormality. So what will happen? The time of these fundamental heart sounds will in addition to that, be any abnormality, there might be other sounds may also appear, like in between in the systole period or in the diastole period, which are called as murmur sounds, right? Systole period is the period from S1 to S2, and diastole period is period from S2 to next X1. Now, if we can identify that these abnormal sounds are available in the systole period, we can likely to identify which kind of stenosis or which kind of disease is there according to the period also. And in a particular period, considering various frequency characteristics and the time and the envelope characteristics, we can say that there is a probability of this particular disease. That's why if we analyze these heart sound signals for a long term, we can extract meaningful features to detect the various cardiovascular disease at an early stage. But the point is to perform the long-term monitoring of the heart, the system is required which can be applied in the real life, right? When I'm saying in the real life or daily life scenarios, that means the system should be able to deal with the noises present in the real life applications. So the most important task in this particular field is how to deal with the various noises. What is the challenge when we are going to deal with the presence of noise? We can understand with this particular figure. Is there any message? Is there any doubt till now? Okay. So I have kept the first two figures of two abnormal categories, specifically the aortic stenosis and mitral stenosis. And then there are three signals. These are three normal signals contaminated with three different simulated noise: synthetic noise, red noise, pink noise, and real life noise. Now, what I want to say is that there is little bit similarity between the characteristics of the noise as well as the characteristics of the noise as well as the characteristics of the abnormal signal. This is one scenario. Another challenge in handling these noise is that these noises overlap the heart sound signal, the fundamental heart sound signals in the time and frequency domain both. And therefore, it becomes very important to process these signals in time frequency domain. So I will discuss two techniques which we have used till now to process the heart sound signals in the different time and frequency domain. And then we have how to process them in the real life noises. So I'm going to discuss one of the technique first based on the discrete wavelet form. You might be aware about this particular technique, which is the denoising. Might be aware of the transform. Here there are three steps. In the first step, we decompose the signal. In the second step, we perform the thresholding, and in the third step, we perform the reconstruction. Okay, I will give a brief about what happened in these three steps. High pass filter and low pass filter on the signal. So if the signal in these two arcs, let's say if I apply these two, out of these two filters would be like high pass filter will contain 250 to 500 hertz and low pass filter will contain 0 to 250 hertz, right? You should observe that if I will retain both the output filter, the number of samples will be double. The number of data will be double. But if I will follow the Nyquist rate without losing information, I can downsample these two outputs by a factor of 2. And that's why we we downsample these outputs by a factor of 2. And that's how we get a detail level coefficient. The output of the high pass filter is called as detail level coefficient. The output of low pass filter is called as approximation level coefficient. If we want to decompose the signal further, what we can do, we will apply the same process on the approximation signal of the previous level to get the detailed and approximation level signal at the next level. So we will apply as many decomposition levels we want to achieve. Once we decompose the signal like this, we will apply the thresholding. Thresholding is the process where we would like to treat the coefficients, obtained coefficient, such that we remove the noise and then we reconstruct the signal. After the thresholding, in the reconstruction phase, we apply again two of the filters, high pass filter and low pass filter. These are called as synthesis filters, and then we recombine them to get approximation level, and then again approximation, and then again we apply this on the approximation and the previous level. This is a typical. These are the typical steps followed when we are approving. This is the because we have to understand that there are certain characteristics of the heart sound signal, there are certain characteristics of the noise, and to want to perform the thresholding, and that's what I'm going to discuss in the further slides. Before that, to understand that what kind of techniques we can devise to process a heart sound signal, this is describing a decomposition of normal heart sound signal up to 5 levels. Level 1, 2, 3, 4, and 5. And we also get one approximation level signal, as I mentioned. Since the sampling frequency of the original signal is 2 kHz, so according to Nyquist sample, the maximum sampling frequency can be 1 kHz in this original signal. And as I mentioned, if the original signal is having 0 to 1 kHz, the detail level 1 will contain 500 to 1 kHz, and approximation will contain 0 to 500 Hz. Now we are decomposing it to further. So level 2 will contain the frequency range further from 250 to 500. Level 3 will contain 125 to 250 and so on. And finally, the approximation level will contain 0 to 31 Hz. Now, how to take a decision? Let's say if you are working on in a different domain, not on this Hertz sound signal, then how to identify how many levels you should decompose. To take that decision, you have to first, okay, now there are two decision points. One is how to select the mother wavelet. In this particular example, we have used the CoF 5 as a mother wavelet and we have decomposed up to 5 levels. To select a mother wavelet, now there are two decision points. One is that there are certain properties of the mother wavelet, like the vanishing moment. Is the mother wavelet orthogonal, bi-orthogonal, or so on? Is it continuous in the gradient descent or not? If you are applying the optimization thing, then you have to consider those things. So one thing is that we can consider certain characteristics of the wavelet mother wavelet to take the decision which kind of mother wavelet we should use, and we can also consider the experimental available in the literature. Regarding the number of levels, see, we pick level 5 because after analyzing, we understood that Hertz sound signals are prominently being present in level 4 and 5, right? If you will analyze the amplitude, the prominence is in the 4 and 5, you know, and rest most likely in the higher frequencies, the noise will be more, and again, the low frequency range is also contaminated with motion noise. So that's why we pick the decomposition up to 5 levels. Now, once we have decomposed the signal, next task is the thresholding. In general, in the literature, various methods are available to interpret these are the properties which thresholding. Like the rigor sure, spiral loop, heuristic sure, minimax, and so on. These keywords I have picked according to the inbuilt library available in the MathWorks. There might be different terminologies in different libraries, but these are the formulas. I'm not going into much detail how these are being calculated. But the point is, as I mentioned, we have to understand the characteristics of the particular signal, and then we have to devise a new thresholding technique. So for that, we analyze the Hertz sound signal into 3 different scenarios. In the low level of noise, in the moderate noise, and the high level of noise. We analyze 3 statistical parameters: mean, median. Here it is median 75. I will discuss what is that, and variance. And please also observe we are calculating mean, median, and variance on the absolute of the signal, not on the original signal. Now, what is median 75? Median 75 is 75th percentile value of sorted absolute value of the signal. So in general, we use the median of the signal, which is 50th percentile. Here we are using 75th percentile, and there is a specific reason. The reason is, if you will short this Hertz sound signal, right? If you will short this Hertz sound signal, what will happen? In a normal Hertz sound signal, the duration of S1 and S2 is typically around 20% of one cardiac cycle. That means the 25th percentile value is most likely indicating the level of noise, right? And that's why we use the median 75 instead of median 50. Now, we analyze the behavior of these 3 statistical parameters in these 3 different scenarios. Please observe, in the first scenario where the level of noise is very low, median 75 is lower than mean and variance both. When there is moderate noise, median 75 becomes greater than variance but remain less than mean. In the third case, where the level of noise is very high, the median 75 becomes greater than mean and variance. So we plot these different statistical parameters with respect to the SNR values after adding the white Gaussian noise in the signal, and by analyzing the relationship between these statistical parameters in these 3 different cases, we form a particular thresholding function for these 3 different cases based on these statistical parameters. But the idea is simple, that according to these 3 different cases, we understood that how these parameters behave, and accordingly we devise a particular thresholding method. Next task, once we have estimated the threshold value, next step to apply this threshold value on the coefficient. Now, these are two popular methods. One is called a soft threshold function, another is called as hard threshold function. In case of soft threshold function, the coefficients lower than threshold value get reduced by that particular amount, threshold amount. While in case of hard threshold function, whatever the values are there, lower than the threshold, they will be zero, rest will be unchanged, right? What is the issue between with these two is that in case of soft thresholding, although it produces significantly good results, but the point is, it is also attenuating the important diagnostic parameters. While in case of hard threshold function, due to this discontinuity, when we reconstruct the signal, there would be discontinuity in the reconstructed signal. To avoid this scenario, we propose a new thresholding method called mid-threshold function, which is based on two parameters, alpha, beta, and a third parameter, the threshold value, which is estimated according to the previous formula. And then we perform the thresholding of the coefficients. We got certain values of the alpha and beta experimentally, but to perform the optimization, to get an optimized value for the heart sound signal of these alpha and beta values, we performed the genetic algorithm and we got these values for alpha and beta according to the relationship of the statistical parameters. I will briefly discuss the results. Those who are interested, most likely I have shared the reference link of the particular paper where we have presented these results. So I will quickly skip the results, just describing this particular slide. In this slide, please observe this is the clean ECG signal. We added white Gaussian noise. So this is the signal after adding the noise. And all these things are the results of various methods, right? These are the methods of various existing methods, and the last two rows are the results using the proposed method. Now, please observe from this signal, the signal fed to the model, to the denoising algorithm, we obtain this kind of signal, right? That means the devised algorithm for the denoising of heart sound signal effectively remove the white Gaussian noise. But the point is, generally the real life noises do not follow the characteristics of the white Gaussian noise. So it is important to test your denoising algorithm with various, most likely with the real life noise, also with the synthetic noise, which are having frequency characteristics close to real life noises, right? And that's why we consider the red noise and pink noise. This is the link of the particular paper where you can find the detailed results of this particular method. I will share these slides with the organizer. I will request to the organizer, they can share these slides with the participants. These are the results for the pink and white red noise. As I mentioned, if you are devising a particular denoising algorithm, you should you should test your algorithms on various synthetic noises of various real life noise characteristics. And also we applied the algorithm on the signals acquired in the real life scenarios. And we observed that the method was really working very effectively. Then also we apply the method on the signals, on the abnormal signals. Although this is not the final motivation to remove the pathological sounds. As I mentioned, there are the murmur sounds, which are the pathological sounds. So this is not the final objective to remove them. But the point is, if we can remove these murmur sounds and if we can detect the S1 and S2 very clearly, these are the fundamental heart sounds, we can easily identify which one is the systole period and which one is the diastole period. Once we know the systole and diastole period, we can say the murmur is present in the systole period or diastole period. Is it holosystolic or a click, right? So according to that, we can provide more diagnostic information if we know what is the location of an S1 and S2. And that's why we try to remove the pathological sounds here. Now I will discuss one more technique to deal with the noises and to be how to also means to overcome with the pathological sounds. This is the flow chart of this particular method. What we are doing? We are doing certain processing steps. Then we are applying the another time frequency analysis technique called as tunable quality wavelet transform. I will discuss little bit concept and the comparison of this TQWT with the wavelet transform. I will discuss what was the decision point in this particular technique, how we can address the denoising, then the segmentation of the signal, feature extraction, and finally the classification using some classification, classical machine learning tools. This is the reference of this particular work. You may follow this one. Okay. As I mentioned, in case of DWT, we were applying two steps, right? We were in the decomposition, we were applying the filtering using the high pass filter and low pass filter, and then we were applying the downsampling, right? In case of tunable quality wavelet transform, we apply these two steps in also, but in a little different manner. So if you will compare, we will observe this figure. Please observe on the original signal. On the original signal, we are applying high pass filter and low pass filter. In case of wavelet transform, as I mentioned, the high pass filter will divide the frequency range of the original signal into two parts, pi by 2 to pi and 0 to pi by 2. In case of tunable quality wavelet transform, the frequency range of a particular filter will depend on certain parameter beta and alpha. What is that? These alpha and beta parameters are obtained using two other parameters called as quality factor Q and redundancy factor R. So we have to identify the values of Q and R. Once we have identified these values, the value of beta and R can be calculated using two formulas. And then we can identify what will be the frequency range of particular output at a particular level. Once we have applied these filters, we are going to apply the scaling. In case of wavelet transform, I call that downsampling. Here I am calling it as a scaling, sampling scaling. In case of wavelet transform, the factor was 1 by 2. We were downsampling the signal by factor of 2. Here we are going to downsample the signal by factor of beta, right? In case of low pass filter, the downsampling factor would be alpha. So these are two changes. Steps are same. We are applying high pass filter, low pass filter, and then we are applying the scaling. But in case of tunable quality wavelet transform, the range of a particular band depends on the alpha and beta parameter, which are identified using the values Q and R. What is the advantage of this? The advantage is that in case of wavelet transform, we can, let's say at level 2, we cannot control the frequency range of level 2 band if we are decomposing a signal using wavelet transform, right? It will be from pi by 4 to pi by 2 typically. But according to the application, I want a different frequency range. Using tunable quality wavelet transform, I can do that. And that's why there is a term called tunable. I can tune the quality factor. And the quality factor is the ratio of the bandwidth of a particular band with the center frequency of that particular band. So this is the tunable quality wavelet transform. In this particular work, we have used the tunable quality wavelet transform using certain parameters. There are two ways to identify these values. One is the empirically. You have to conduct the experiments to identify which are the suitable things. And second thing, to analyze the literature survey, what kind of other works have used these values. We have used these three different values and decomposed the signal up to 16 levels. Okay, I'm skipping the complete means the nitty-gritty how to exactly perform the decomposition using the identity frequency band. Go to if you reference but the basic idea the decomposition and this to the DWT, but we are using here alpha and beta. Okay. So if you want to identify the bandwidth of a particular frequency band decomposed using tunable quality wavelet transform, we can use this particular formula. and calculate what is the bandwidth covered by the bandwidth level J. We can frequency at that particular level J. This is the reference. Those who are interested to implement this tunable quality wavelet transform, I will suggest you to go through this particular link where you will find the implementation of this particular technique through the MATLAB. Now I'm going to discuss what are the different other decision parameters when you are going to deal with the various heart sound signal scenarios. In this particular example, this is a particular signal of one pathological case. We have decomposed it up to 16 levels. So we obtain the 16 detail level coefficients and one approximation level, which is not being shown here. Now please observe, in the 16 level mostly, the S1 and S2 are prominently available, right? Compared to the murmur sounds, the S1 and S2 are more prominent in the level 16. But the point is, in different pathological sounds, the frequency range of S1 and S2 will change. What will happen? Due to that, in which particular band the S1 and S2 will be prominently available, that is not fixed. In this case, it is 16, but in another pathological case, let's say it might be 12, or it might be 8, or it might be 15. So now the challenge here is that how to identify which particular band you should select to process further. For that, we did a little bit literature survey. There were particular factor called kurtosis, which was being used for this particular purpose. However, we observe certain limitations of the kurtosis. This particular graph is describing the behavior of the numerator and denominator term of the kurtosis with respect to SNR of the signal after added wide Gaussian noise. Please observe, with the increment of the noise level, the numerator term is decreasing little bit and denominator term is almost constant. That means kurtosis value will decrease as the wide Gaussian noise will increase, right? We did little bit experiments and then come up with a different formula and then identified that this is a well-known factor called Fano factor in different domains. If we analyze the numerator and denominator term of the Fano factor, we can analyze that the numerator term is gradually decreasing with increase in the wide Gaussian noise, but the denominator term is exponentially increasing with the increase in the wide Gaussian noise. So finally, the Fano factor will exponentially increase as the level of noise will increase. So it is expected that the Fano factor will indicate the level of noise more accurately compared to kurtosis value. Therefore, we use the Fano factor for this purpose to select a particular band to process further. To understand the impact of the kurtosis value on Fano factor, this is one example which is describing the subbands, the bands obtained using the tunable quality wavelet transform for aortic regurgitation and aortic wall ejection. In the first case, the kurtosis value and the Fano factor value is higher for level 2, right, compared to level 1. That means both the factors, kurtosis value and Fano factor, will say that level 2 is having prominent heart sounds, and that is true, right? But in second case, please observe that the kurtosis value is higher for level 1 and the Fano factor is higher for level 2. That means if we select the kurtosis value, then level will be selected, level 1 will be selected, and if we will use the Fano factor, level 2 will be selected. And it can be observed that the level 2 actually have the prominent heart sounds compared to level 1. That means empirically, we also identified the Fano factor is providing the better result compared to the kurtosis value. Once a particular subband has been selected, we perform the denoising using the same technique we devised in the previous technique. We use this threshold estimation method and we use the mid threshold function to perform the thresholding of the obtained coefficients at a particular level. Next, once we have we have denoised the signal, we segmented the signal using a well popular technique to perform the segmentation of heart sound signal, which is based on Markov model called as hidden semi-Markov model, proposed in this particular reference by the Springer and other in 2016. After the segmentation, we extract, as I mentioned, the time and frequency characteristics of various components. S1, S2, and the systole period and diastole periods provide the diagnostic information. We extracted various time and frequency domain features after the segmentation, and then use these features to train the classical models. For the classical models, we consider the support vector machine, k-nearest neighbor, ensemble methods where we use the boosting trees, baked trees, subspace Cannon, and subspace discriminant analysis technique. This is the particular data set we have used for this experiment, where there were 5 categories of the abnormal signals were there. These are the number of for each particular category. And these are the results obtained using all these 4 methods we have used. So this is the method, these are the results obtained using the SVM with different kernel functions, linear, quadratic, cubic, Gaussian, and so on. Again, I will quickly summarize these results using the table. Means you can go through these results and analyze these results through the particular reference, and then if there would be any question, you may contact me further. So the point is, according to this table, the significant results obtained using the SVM when we use the kernel function quadratic. Then we apply the Cannon method. We apply the various ensemble methods, and finally we compare the proposed methods with various methods available in the literature, and this is the comparison. So the best results for the proposed method obtained using the ensemble Cannon, and the best result was 99.04 for the 5-class classification problem. And you can understand with this particular table, you can observe this with this particular table that the results of the proposed method were significantly improved compared to the existing state-of-art methods. Although means I will specifically comment about these dataset, about the work, and those who are interested to work in this area, what are the current challenges, current available data sets, and so on. So please don't worry about it, right? Now I will little bit discuss about one basic approach I tried using some deep learning models, although means I could not update these slides for a particular method. We have implemented some particular deep learning method where we combined the CNN model or sequential model. One is the GRE model, and where we obtained the more accurate results. Simply, this is a very basic technique we have used here, is that instead of applying the signal directly to the particular deep learning model, what we did was we converted first the signal into the coefficients, or you can say in the multi-resolution domain, using the DWT decomposition, and then obtained coefficients have been used to train the 1D CNN model. We use the same data set as I mentioned in the previous example, which is composed of the 5 different levels, 4 abnormal categories and 1 normal categories. These are the few steps which we have followed. The simple steps like the resampling, normalization, resizing. Okay, so please observe, this is one challenge in this particular data set. This is the data set generally called as Yasin Khan data set. I will discuss in detail all those 5 available data sets. But this is the data set where there are 5 categories available. For each category, there are 200 samples. The point is there are 3 cardiac cycles available in each sample. But the issue is that with respect to different heart rate, the duration of these 3 cardiac cycles are different, right? Now, if we are not going to rescale them, probably the model will understand that the frequencies are different in different signals with respect to heart rate. So it is important to rescale the signal with respect to heart rate, right? So this is one step we did before decomposing the signal using DWT. After the rescaling, we decompose the signal up to 5 level. As we have discussed that we observed that this kind of 5 level decomposition is helping us to get the better results. There is one specific region as I have already pointed out, that by decomposing in this way, the fundamental heart sounds falls generally in the 4th level and the 5th level, and the abnormal heart sounds and the noise falls in the detail coefficients, which can be dealt separately. And so we use these coefficients, obtain coefficients using the DWT to train the a CNN model, very basic CNN model where we just use the two convolutional layers. We just frame this kind of CNN model and train with the space just to see that can a basic CNN model produce a significant result. And based on the obtained results, we can say that the basic CNN model using the DWT coefficient, the trend on the DWT coefficients is able to achieve significantly good results, right? The accuracy is close to 98.9, which was in earlier case it was close to 99 point something. So we can say that this is means a significant result we obtained with the basic model. So till now, if I will conclude all these results, these are few conclusions. One is that algorithms to classify the heart sound signal based on the multi-domain features in machine learning techniques has been presented, and these are prominent. So one first thing is that it is the prominent task to convert the time domain signal into time frequency domain, because the time and frequency characteristics of these signals are important for diagnostic purpose. And as of my knowledge, in most of the signals, the time and frequency characteristics are important, and that's why researchers in the current domain now trying to first convert the signal from the spatial or time domain into time frequency domain, and then they are using those kind of either scalogram images or the coefficients to train the models further. Next, we observed that even the basic deep learning models based on the CNN can achieve very significant results. Although I will say this is kind of limitation with the data set also. I will comment on that in the further slides when I will discuss the data sets. Importantly, means why the results were satisfactorily using the proposed method. One is the use of the tunable quality wavelet transform. As I mentioned, this particular method provides the ability to tune the quality of the wavelet transform, and due to that we can set the frequency range of particular band by identifying empirically which is more suitable to separate the fundamental heart sounds and the pathological sounds. And second, the inclusion of the time frequency domain features, the extractor features were able to distinguish the normal from other pathological cases. It is also observed that the classification of heart sound signal as normal or abnormal can be performed more accurately compared to the classification of a specific disease. The point, what is the important point I want to highlight from this conclusion is that, see, the main requirement in the current scenario is that if you want to perform, let's say, the early stage detection, for the early stage detection, there should be a system which can be used by the subject without the intervention of a medical person, because you can understand in the developing countries like India, the medical facilities are in the scarce, and the expert cardiologists are very low in the number as compared to the required number, as suggested by the WHO. Therefore, it is required that the system should be able to work in the real life scenario, so that the user can use it in let's say at home or at a workplace without visiting the clinical scenario. And the user should be able to detect the disease without intervention of the medical person. So first thing is that there should be a robust to noise system which should be able to detect any abnormality at an early stage. At the user end, there is it is less likely or less meaningful which kind of abnormality is there. Let's say even the user know that, let's say there is aortic regurgitation or the aortic stenosis. Even in that case, user cannot initiate the medication without the medical intervention. So the point is, users should be able to understand that is there any abnormality. If there is an abnormality, in any case, he has to visit to the medical person, where these kind of machine learning techniques help the medical person further to improve the accuracy of the diagnosis. So that's why it is important that if the models are able to provide the significant results for the normal versus abnormal detection, that would be very helpful. And that's what I want to highlight here. Now, as I mentioned, I specifically kept a few slides to discuss the future scope in this particular domain. As I mentioned earlier, there are certain techniques to analyze the cardiovascular functionality with various different sensors like electrocardiogram, phonocardiogram, and I used the one term called accelerometer, right? And the technique is called as seismocardiogram. See, in case of seismocardiogram, recently now the MEMS accelerometer are being used, and the size and weight of the accelerometers are very low. MEMS accelerometers are very low and very suitable for long-term monitoring, so that we can attach those accelerometers for the long term to the user, and we can monitor the heart functionality without hampering the routine activity of the user. That's why means right now the researchers are focusing much on extracting the important features from the seismocardiogram signal. So this is one future direction where means many of you may work. Exploration of seismocardiogram for various cardiovascular disease, including the valvular disease and myocardial infarction. Recently, means earlier there were no database available publicly for this particular thing, but recently in 2022, now there is one particular data set. I have not mentioned that particular link here, but if you will search the database for the seismocardiogram with various abnormalities, you will find that one. Next, as I mentioned, there is a vast field to explore various time frequency domain techniques to analyze the heart sound signals. People are trying various time frequency analysis techniques like wavelet transform, tunable quality wavelet transform, Stockwell transform called as ST transform, wavelet synchro squeezing transform, uh, wavelet scattering transform, and there are various transform techniques, time frequency techniques, which have been used. Some of may have been used for that sound signal, some of are being used for various other sound signals, but can be used for the heart sound signal also. So this is one dimension where the future research can be focused on. I have not discussed means one of my recent work, which is to assess the quality of heart sound signal. This is very interesting and the important requirement, as I understand. The point is, when we are recording the heart sound signal, let's say for 1 minute, uh, to analyze the heart signal, we do not require, let's say, 70 or 60 cardiac cycles, which will occur in 1 minute typically. We only require hardly 5 or 10 cardiac cycles. And if we are recording in the real life signals, or even in case of clinical signal also, it may happen that there are certain parts of the signal which are clean, and there are certain parts which may contaminate with the noise due to various factors. If we can have quality index, we can extract the particular segment, sub-segment from the signal where the signal is very clean. And that's why now, if you will go through the literature in this particular domain, you will find that these researchers have started identifying certain quality indices for the heart sound signal. In the number, I can say around right now there are around 5 to 7 attempts, right? That means you can understand that this is a kind of hot topic in this particular domain. Another thing is that you will find that researchers are now starting to use heart sound signal to classify the myocardial infarction. Sorry, infarction. Yeah. Although I have mentioned the infarction for means when I have discussed, but the point is generally heart sound signals used for the heart valve disease. Uh, Publicly, there is no specific data set available for myocardial infarction disease using the phonocardiogram. But right now in 2021, I will discuss that particular data set probably in the next slide, where there are certain samples available of the heart sound signal contaminated or having the abnormality of myocardial infarction. So now means the people are working in this particular problem now. These are few papers. Those who are going to start working in this particular domain, I have just kept out. I have just figured out few papers to start with to understand the basic modalities, to understand what are the current challenges, and so on. And at the end, these are the few databases. As I mentioned, whatever the experiments I have explained are on this particular data set, although I have used this particular data set also for various other experiments, I could not share those various other works with you guys with this particular short domain. Probably we are means more than 60 minutes we have crossed. So I will just, okay, I will just discuss what are the basic challenges in this data set, what are the basic characteristics and the limitations in data sets. So those who want to start working in this particular direction, how they can start. First of all these 5 data sets are publicly available. The most important data set which is considered is the first one available at the PhysioNet website. Those who are working in the medical field or specifically in the signal processing, medical signal processing, you should visit this particular website, PhysioNet Challenges. This is a particular website where they float challenges for every year multiple times in different domains, in different modalities. This was one particular challenge on heart sound signal in 2016, and then they updated in 2021 also. Earlier, there were only 2 categories. In 21, they updated the various categories. However, means people are not much considering those categories because the numbers are very low. But with respect to normal and abnormal, although there is a class imbalance, that is one major issue in this particular data set, but the number is adequate, right? 2,575 for normal and 665 for abnormal. In this particular data set, what is the major challenge? If anyone want to work on this particular data set, as of my knowledge, I would suggest to use certain quality parameter. Why is that? There are many recordings which are varying from 5 seconds to 5 minutes, right? That means 5 seconds multiplied by around what 12 cross 5, 60 times. You know? So the duration is very widely ranged. As I mentioned, we only require a very specific segment, let's say 5 second or 10 segment data to perform the diagnosis. And in this particular recording, which included the real means the clinical setup recording and out of clinic setup recording, there are certain phases where there is a very high noise and there are particular phases where there is a very low noise. So if you want to use this particular data set, the quality index becomes a very important factor. Certain authors, if you will go through the literature in this field, certain authors have used the quality index for this data set, but many of them are using the first 5 second or 10 segment of the particular data set. So that is one challenge in this particular data set. In data set 2, the issue is that the number of recordings are very low. Second thing is that they have mentioned, instead of mentioning the abnormal categories, they have mentioned the type of the heart sound, extrasystole or the murmur or normal. So there means there are only few papers on this particular data set. Then again, another popular data set in this particular direction is by Yasin Khan data set. As I mentioned, whatever we have used, whatever the results I have discussed in this presentation, it is composed of 5 different categories. Each category is having 200 recordings. Mostly recordings cover 3 cardiac cycles. What is the issue in this data set? The abnormal signals are very clean, right? And that's why you can observe that if you even if a very simple deep learning model is able to achieve 99 accuracy, close to the 99% accuracy, that means you can say that this data set is almost kind of saturated. So if you will go through the literature survey in the recent past, you will find that most of the papers are now coming up with the accuracy close to 99, right? That means now there is a very less scope to work with this particular data set. Although, if you want to work with this particular data set, since the issue is that with the abnormality, this is the prominent data set, people's what researchers are trying to do is that they are incorporating the noise with this particular data set, and then they are considering that how to deal with the noise in the presence of the abnormal categories, and then to perform the classification. So that is one open problem with this particular data set if you want to explore further. Again, there are these two popular publicly available data sets, but not much popular. There are certain papers which were come up, but not in the recent past. I'm not observing those things. So in conclusion, I will say I have specifically mentioned certain future direction, the research possibilities in this particular area, the available public data sets. That's it. So I will stop here. I will open the session for the question and answers.
Thank you, sir. Any question is there? Anybody? If you have any question, then please come here.
Yes, is there any question?
Yes, sir, we are asking.
Okay, well,
If anybody having any question, then please come on a stage and ask, because the mic is here. And there also. Yeah, yes, yes, please ask. You ask, sir, na? Please come. Please come, please. Please come. No issue, no issue. Come, I am also staying. Just ask the same question. What question?
Sir, this is just a simple question that whether you have the specific laboratory in your institution. That's all.
sorry, I
You
could
have
not get
the
your question.
specific dedicated.
Okay, sir, he is asking, is there any laboratories there in your organization related to this thing?
Yeah, so right now it means I have means working project. So regarding that, we have developed the systems to acquire the signals in my laboratory. Acha, regarding that, okay, I will suggest means if you want to record your heart sound signal, let's say using the stethoscope or using this accelerometer, to record the signals, you will have to expend around 1K or at max 2K, right? 1000 or 2000 Indian rupees. So those who want to do that, let me share that simple. What I will first suggest you is that you can go through any one of my paper. You can find through my profile also, or you can message it to me. I will share those papers. I have mentioned that I am how I am acquiring the signals. You can do it very easily. It's not a complicated task. At least for the PCG, SCG signal, and now there are certain means already fabricated PCB for one lead ECG signal recording, and all these systems will cost you around 1000. So those who want to record it, you can record it very easily. So it's not like that these facilities are available only in my laboratory and you will have to do that. But yes, if you want to visit my laboratory at any time, you can contact me further.
Yes, sir. Sir, one more question.
Yes.
Please come. Please come. Participate is coming.
Hello, sir.
Yes.
Hello, sir. Good afternoon.
Yes, good afternoon.
Yeah, sir. My name is Ravichandra. I'm doing PhD in Anna University, Chennai, Tamil Nadu, sir.
Okay.
Actually, my title is Authenticated Detection of Vulnerability Behavior of the Implanted Pacemaker.
Vulnerability
hear me, sir?
about?
Yeah.
Sorry,
Can you- Yeah, my title is Authenticated Detection of Vulnerability Behavior of the Implanted Pacemaker.
Okay, okay.
Now I have completed my coursework and also completed my confirmation. I started developing my research work. Actually, the title of novel-based detection of cardiac arrhythmias using CNN and LSTM.
Great.
Yes. Here, I have been using the Physionet MIT BIH dataset,
Okay.
in which I have found only that limited version, limited data sets are available. For example, if I want to find out the left bundle branch block means, I can get only modified L2 with L1, sorry, with V1.
Hmm.
In practical life, it is not enough to diagnose the LBBP.
Yes.
Actually, doctors, medical practitioners are using to diagnose the LBB by making different combinations of ECG leads like L1, L2, L3, AVR, AVL, AVF, and VM2, V6 series. There may be some certain limitation out there, but still that modified L2 and V1 is not enough to diagnose perfectly to enhance my accuracy. What can I do for that?
Okay, yeah, means I can understand your problem, and this is the general problem. I can tell you. Although means I have not much explored the processing of the ECG signal, but I am in the team where probably if you are interested, if you are working on the ECG, you should follow that particular profile. There is one particular faculty called Sivaraman Jain, right, in the biomedical department, NIT Rourkela. He specifically work on the ECG signal, and with that, I know that your point is means perfectly right. What is that in publicly available data sets, there are specific problems. Although those specific problems are also genuine. That means if they are saying that let's detect disease A with using these leads. So yes, that's fine that we can perform the disease with those leads. But even for myocardial infarction, we were trying to identify that we are in the collaboration here with a particular hospital, and by analyzing those signals, we observe certain other certain other characteristics. You can follow those papers. You will find that how we are doing that. So yes, your point is right that there are various other characteristics available which the medical persons use to diagnose and which are absent in the publicly available data sets. So that is yes, that is kind of limitations for the researchers.
Yes.
But
There are
the solution for that is that we have to figure out that can we obtain the signals from the medical person, because for the abnormal subject we can only get the signals from the medical person only. So yes, that is a genuine problem. Yeah, regarding the data set, any data set, of course, means as I mentioned in case of heart sound signal, I have mentioned there are various limitations of all these data sets. Whatever the data set you use, there are certain limitations.
Also duration of that data set. Duration.
I will not say that the duration is the major issue, but yes, the major issue is that one is the generalizability, the publicly available data sets are very limited in the generalizability. They are very specific to specific scenario. And the second thing is that they have a specific kind of characteristics. They are not focusing on other characteristics which, let's say, the Indian medical persons are using those kind of characteristics. So that is not available. Yeah. And not only in case of ECG, PCG, not in case of ECG, PCG. Let me say, one of my PhD scholar is working on brain MRI images. So again, in that case, we are facing that issue. Again we are in the collaboration with one more medical person for that particular problem. Means whatever the characteristics they are using to analyze, to identify those lesion parts, many times it is absent or not available, the ground truth not in line with their observation. So if we will train the model for the publicly available data set, it may fail in the real life.
Yes, sir.
Yeah, so that is the issue. Even again, means there is another thing that even we are getting our data set, still we have to train our model on the publicly available data set, because if we have to go for the publication, we have to show that our method is performing better than other methods. Then we have to show what kind of data set they have used. We have to use that data set also. So
Yes, sir. Yes.
these are the things we have to consider when we are doing the research in this medical field.
Yes. That's all. Thank you, sir.
Anyone, any more question? Anything more? I observe no question is there. Oh, one more question, sir.
Yeah.
Hello, sir.
Yes.
Thanks for your valuable talk. I'm Vivek Pandey here from IIT Mesra. And I have a question regarding the non-stationary signal as ECG, PCG, all signals are non-stationary signals. So what I'm I'm doing focus about the feature extraction techniques, as you have explained in TQW2 feature techniques over here. But what is the pre-processing for these non-stationary signals that we can focus for new era concept when our research paper will early accepted?
You are talking about that what kind of pre-processing we should do before the time frequency analysis domain transformation.
Yeah. Actually,
Okay.
we have. Yes, sir?
Yes. Do you want to ask the pre-processing steps before the transformation in the time frequency domain?
I'm asking about the feature extraction techniques where we have used in some non-stationary signals in pre-processing concept.
So, first of all, the pre-processing steps will depend on the characteristics of the particular signal available in the data set. Like as I mentioned, in that particular Yasin Khan data set, there were certain issues. So the pre-processing steps will depend accordingly. Like in case of PGONet data set, the pre-processing step would be the quality assessment and the sub-segment selection. So first thing is that the pre-processing steps, I cannot say that there would be a unique general pre-processing steps, except few normal like bandpass filtering and normalization and so on. The pre-processing step generally depends on what kind of data set we are using and what kind of problems are available. But I can suggest this on second step, which is the time frequency analysis technique. Regarding that, I have already I named few time frequency analysis techniques. If you want to deal with these time frequency analysis techniques, first of all, you have to understand the basics. For that, I will strongly recommend. Right now, there is one particular book. I was struggling for that particular book, but right now there is one book by Professor Ramvilas Pachori from IIT Indore. It is available on the Amazon. You can buy that particular book on the time frequency analysis and applications. Rest, you can follow this particular tagline means if you will follow this time frequency analysis techniques, you can say you will find that people are using various time frequency analysis techniques for various domain. If you will only follow the research papers in your domain, what will happen is that that particular technique is already have been used for your purpose. Then what for you the optimization would be very restricted. But if you will keep open the domain and you will search for the time frequency analysis techniques, let's say for the signal, many times there is a vast research going on to speech signal processing. You will find n number of time frequency analysis techniques proposed for the speech signal processing. Now understand them, figure it out. Is it suitable for your signal? Can we apply that? And then we have to find out further steps. Again, after the time transformation, what kind of steps you have to perform will depend on the data set and the problem. Let's say in this particular case, what I have discussed, the problem was to segment the signal. We were performing the thresholding. If the purpose is not the segmentation, we will not apply the thresholding. So those the pre-processing and the post-processing depends on the problem. But regarding the time frequency analysis technique, there are various techniques which are suitable for a specific purpose, right? Like in this particular case, the major issue is that we want some time frequency analysis techniques which are robust to noise. That means even in the presence of noise, the features provided by these time frequency techniques should not vary much, right? So experimentally, I can say there is one recent work on this particular technique using the wavelet scattering method. So that is good, providing very good results. So again, there are two things. One is going through the basics of the time frequency analysis techniques, and second thing is that going through the literature related to that kind of problem, right? So that's how you can figure it out that what kind of steps you can apply.
And thank you, sir, for this. And I have another question is, as per the biomedical field, we have two things. One healthy data set and another is a pathogenic data set that come from patients. So can we interlink with healthy data set and pathogenic data set as well? What is the deficiency between both of?
What you want to say by interlink?
For example, if I'm talking about a ECG signal, ECG
Yes.
has a PQRST waveform,
Okay.
right? And it depends according to the sound, according to the analysis of left article and ventricle in right and left side, right? So some of the deficiencies when it will occur, then the sound analysis of a sound signal will vary according to that particular things. Like tricuspid valve or bicuspid valve.
Do you want to ask your question in that way? Can you use multi-modals to perform the analysis of the particular organ? Like in case of heart, can we use the ECG and PCG both? That's what you want to?
Actually, I would like to know about if I have two signals, like one is a healthy cardiac sound signal, and another one is the pathogenic signal, like a patient is suffering from heart disease. So, and I would like to interlink between both of where is the similarities and where is a non-similar form in that particular waveform by using any concept of or any methods that can extract these type of things. And we can analyze and perform, yes, this situation is going to particular disease. Like a pattern, I would like to take the concept of pattern.
Totally, I got your question. You want to understand that can we analyze normal versus abnormal signals so that we can diagnose, we can classify them, right? So
yeah, exactly.
There are two things. One thing is that one particular algorithm I have explained where we were trying to extract the features, right? Although I did not went into much detail what kind of features we are extracting, but we are extracting certain time and frequency features. Now, how we identified that what kind of time features, what kind of frequency features, what should be the band of those frequencies, how we identified that? Now there are two things again. we empirically identified by analyzing the signal into time frequency. So first of all, before starting your research, I always suggest to my lab mates to first understand your data set. When I'm saying that, let's say this is the data set, these are limitations and these are the advantages. First of all, those points should be clear in your mind that these are the characteristics of the normal signal. These are the characteristics of the abnormal signal. Now, then you can only take a decision that this particular technique will be helpful for me to extract these patterns, right? Suppose, let's say, if I will say, let's say, if I want to segment a particular image, there is particular object with, let's say, black color and the background is white. Very simple scenario. Then first of all, I have to observe the object I want to segment. Is there any specific characteristics of that? In this case, there is a specific color of that object, right? Once I have identified that particular characteristic, I will identify what kind of parameters will be helpful to extract that characteristic. So I will try to identify the parameters to extract the color. And based on that, I will train a particular model, right? So we have to understand the data set first. We have to compare a normal versus abnormal in the time domain, time frequency domain, multi-resolution analysis, understand the data set, understand what kind of characteristics are there with the normal and abnormal data, and then we can do that. If you want to ask your question in that way, you can also use some kind of correlation analysis techniques. By doing those correlation analysis techniques, you can identify which particular signals are more close to each other, which are not, and what are the different parameters which are separating those. So you can do kind of principal component analysis and the support vector decomposition to identify the prominent component, although they will not provide the specific time and means relevant characteristics, right? But they will provide you kind of vectors which are prominently separating normal versus abnormal.
Thank you, sir.
Any other questions?
Any other questions from participants? Okay. So, sir, one more.
Hello, sir. Sir, can we use any unsupervised learning technique like expectation maximization? Or
Yes, I have mentioned we can use unsupervised learning here. Means if you have observed, we were using the KNN, right? So here we can use the unsupervised learning also. But in that case, the important thing is that we have to understand what kind of characteristics we want to extract. Once you have identified the relevant characteristics which are related to the normal and which related to abnormal, you can extract those characteristics, and based on those characteristics, you can apply the unsupervised machine learning techniques also.
Okay.
So based on the clustering, we can do that.
Okay. So I hope, sir, everybody is satisfied now. Last question is from our coordinator, sir. Anurag, sir.
Yes, please. First of all, thank you, Anurag sir, for giving me opportunity to interact with your participants.
Thank you, sir. Thank you very much. It was very insightful discussion. And, I hope everyone has got something. Since so far for cardiovascular analysis, we usually use ECG and all those things. So, but you talk about sound analysis. So I hope participants would have got a different direction to do that task and may develop multimodal sort of analysis like ECG.
Yeah, that's what actually Anurag sir means right now. I did not add that particular point. In the recent past, now the researchers have moved in that direction to use multiple signals like ECG and SCG to understand the electrical, and the term is called electromechanocardiography. So yes, there is an interesting field right now.
Exactly. So because that helps another tool to verify the things, which traditionally we do with ECG. We are having another thing to do to re-verify. So obviously that will help to reassert the findings. So my question was, sir, just a simple one regarding the data which you talked that sound, that heart valve sound. Are you using this existing databases or you are generating your own?
No, for certain part means, as I mentioned, when we have to go for the publication, we have to use certain part of the publicly available data set also. So I'm using that, but like for the data set for the real life scenarios, we are acquiring the signals in the different real life scenarios. We are simulating different kind of noise scenarios. We are acquiring them, and means
Sir,
in the
I'm
publication right
asking
now.
this. Sir, because you talked about that you can make a simple machine like I think stethoscope. You pointed it out like for measuring this heart sound. Can we use? Can we have those type of cheaper option to record the sound for analysis? Just for
Yes, sir.
beginners are.
As I mentioned, under 1K, you can develop your PCG system to acquire your signals. Simple. Let me give you just a let me just give you a hint. Is any conventional stethoscope, generally they cost around 700 to 1000, a good quality stethoscope. Just cut it the tube, then insert a condensed microphone. It will cost you around 20 to 50 rupees if you will buy individually. Attach this microphone with the 3.5 mm jack. So that will cost you around 100, 200 based on the quality. And what you can simply do is that apply this 3.5 mm jack into either to your mobile phone also. Otherwise, you can apply to your laptop or computer system using any particular tool, either MATLAB or Python or any particular tool. You can easily acquire the microphone recording, and that will give you the actual recording.
So have you analyzed this recording, sir? It is like having that information we look regarding that heart sound or specific S1 S2 sound. So like distortion from distortion point of view, I'm asking, sir. It is it's like data is able to process much like further. We are having information proper.
Yeah, so as I mentioned, the major issue in case of real life scenario is that first thing is that the denoising. In case of clean data, the denoising is a critical task. But the more challenging task is that if we want to add the noise. So right now, let's means in the recent work what we did, we recorded the real life noise, because we cannot have abnormal patient here, right? So means I'm on the communication right now to do that. But till now that data set will come. What we are doing, we are using abnormal data set from the publicly available data set. We are recording the real life noise. We are adding this real life noise to this abnormal data set, and then we are trying to denoise it. So denoising of a signal in the presence of abnormality is a critical task, because what happens is that the noise also contaminate in the high frequency range, and the murmurs, the abnormal sounds are also in the high frequency range. So if you will try to suppress the noise, most likely the algo will suppress the pathological sounds, and that's what we do not want.
Exactly.
So that is a challenging task right now we are facing.
Exactly. Yeah. So because data acquisition is a very critical task, and doing on the existing databases nowadays, that is losing its relevance. Nowadays people are at the paper also. If you go, they want what you have done on your data, anything you have created, or anything you have done on practical scenario, real time scenario. So creating our own data using these type of cheaper options that will help us to develop our own problems or solve our own problems. Thank you, sir. Thank you very much for this suggestion or this insightful discussion. Thank you.
Okay, thank you very much.
So I think there is no any further question. So sir, I'm just with your permission, I'm closing this session. Okay, and as a token of appreciation, I'm just through online only. I'm just giving you this small memento, sir. Please accept from
Sir,
our
your
side.
words are appreciation for me, so thank you for that.
Thank you, sir. Thank you very much. We will send it through post. I hope we will be able to deliver you soon.
Okay, thank you very much.
Thank you, sir. Thank you very much.
Okay, sir.
Should I leave the meeting
Thank you,
now?
sir. Yeah, yes, sir.
Okay.
Sure. Okay.